So let's look at an example here of a cascade op-amp circuit. So right off the bat we notice we have two operational amplifiers, one on the left, one on the right. We see that the output from the left amplifier circuit is part of the input to the right amplifier circuit. So with that in mind, we can see that we're dealing with a cascade configuration. And so we can actually go ahead and break this into two separate parts. So if we're looking over here on the left side, we can call this stage 1 of our cascade circuit. And we can then look on the right side and we can call that stage 2. And so what we can do then is we can analyze each stage independently and then combine the results in order to get our overall gain for this circuit. So one thing to note about this example is we see that our non-inverting terminals are drawn on top. So our non-inverting terminals on top. And so all that means is up until this point, at least as far as I recall, all of our examples have been drawn such that we have the non-inverting terminal on the bottom and our inverting terminal on the top. So of course the result of that is that our configurations are going to look a little bit different because they've been flipped upside down, so to speak. And so that's something that you want to be aware of as you're analyzing op-amp circuits. They're not necessarily all going to have the same orientation in terms of inverting and non-inverting. There might be a mix, so you just want to be aware of that as you're solving these circuits. One other thing to keep in mind too is that it's always valid to go back and start at our ideal op-amp properties and analyze the circuit from there. But as we're going to see, it's a lot easier if we can recognize configurations and just plug into those equations that we already have. But again, there's nothing technically wrong with starting from our ideal op-amp properties. So what we notice is if we look closer at both of these stages, we have two non-inverting stages. So we have a non-inverting stage here, and we can tell that because we have an input going directly to our non-inverting terminal, and then we have this resistor to ground and feedback resistor on our inverting terminal. And then we actually have the same configuration over here, so we have another non-inverting configuration here. And we see that the input to our non-inverting terminal of this second stage is just the output from our first stage. Okay, so all we need to do then is go back to our simple equation for our non-inverting amplifier. So we're going to look at the gains of each stage, and then we're going to come and look at both of them together, and we'll be able to find our final output voltage V out. So for stage 1, essentially we can label these resistors like we had in our circuit in the previous video with our non-inverting configuration. This 3K ohm resistor would be like our R1, and this feedback resistor R12 we had labeled as R2. So with that in mind, we can come down here and we can say that our gain for stage 1, we'll call A1, is equal to 1 plus R2, which is 12K, divided by R1, which is 3K. So we plug that in and we get a gain of 5 for stage 1. We're going to do the same process for stage 2. So for stage 2, we now see that we have a 4K for our R1 and a 10K for our R2. So we're going to use those values in that same general equation for non-inverting amplifier configuration to say that the gain of stage 2, which I'm calling A sub 2, is equal to 1 plus R2 over R1, where in this case our R2 is the 10K, like we labeled above, and our R1 is 4K. Plugging that in, we get 3.5 as our gain for stage 2. So we can see that was a lot easier than having to go back and analyze each of those from our ideal op-amp properties. So then we, just in our most recent video, said that, well, the overall gain for a cascaded configuration of op-amps, I'm going to call it A total in this case, or A sub t for A total, we know that's just the product of the individual gain stages, so that's A1 times A2. And we just solve for A1 as 5 and A2 is 3.5. So multiplying those out, we get 17.5 for our overall gain. Well, our input is our 20 millivolts, so now we want our output in terms of that. So we know in general our output is going to be gain times the input. Well, we just solved for our gain as 17.5, and then our input up here on the far left side of the circuit is 20 millivolts, so up here in the top left. So our VI is 20 millivolts, and I can put in 20 millivolts, or I can put in 0.02 volts. If I leave it in millivolts, my answer will be in millivolts, so I get 350 millivolts. So that would be my V out. Okay, so that's half of our answer. We also wanted to know our current I out. In this case, we do not have a load resistor, and so what that means is we're going to have zero current going this way because it's an open circuit. If we're going to have this I naught going through our 10K ohm resistor. Once it gets to this point here, we have zero current going in this direction because we have zero current into an ideal op amp, which means the full value of I naught is flowing through this 4K resistor to ground. So we basically have I naught going through 10K and 4K in series, or 14K. We also have our voltage V naught. We know it's positive at this point, and we know that's referenced to ground. So we have our V naught, which is across the series combination of 10 and 4K ohm resistors. So essentially we can just do an Ohm's law here. So to do that, we're going to say our I naught is equal to the voltage V naught divided by the total resistance, which was that combination of 10K and 4K. And so we say that's sort of in series because there was no current going into that op amp input. And if we plug in the value of 350 millivolts, in this case, if we have, well, again, just be careful with your units in terms of the millivolts and the kiloohms. But what we're going to get is 25 microamps, micro being 10 to the minus 6, of course. So here we're just going to plug this 350 in for there. So again, overall, this analysis we can see was a lot easier and a lot quicker. So right there, just about 7 lines in total, compared to imagine if we had gone back and started with our 2 ideal op amp properties. So again, very important to understand those general expressions for each configuration, how they can be combined into Cascade, and be able to recognize the configurations themselves, even if the op amps are flipped, quote unquote, upside down.